Welcome to the video pitch of On the Workload Dependence of Self-Heating in FinFET Circuits from the authors Victor van Santen, Hussam Amrouch, Poja, Sharma and Jörg Henkel. My name is Victor van Santen and here are the highlights of this publication. In FinFET transistors, the channel is encapsulated within the gate dielectric to improve the electrostatics of the transistor, for example to reduce leakage currents. As a result, the gate dielectric thermally insulates the channel from its surroundings, and the generated heat in the channel cannot be dissipated. Heat is generated inside the channel since a current of a high current density is flowing through a semiconductor, a non-ideal conductor, resulting into Joule heating. As you can see in this material or TCAS simulation from previous work of an Intel 40nm FinFET transistor, solely the channel is hot while both the contacts and the substrate remain close to room temperature. This elevated channel temperature degrades the electrical parameters of the transistors and thus degrades the reliability and performance of the circuit. In this work we study self-heating within a large circuit for the first time. Self-heating is well known in electrical engineering and as such has a large body of previous work. State-of-the-art studied self-heating and more precisely the localized increase in channel temperature on a transistor level. Existing works cover the increase in channel temperature for different technologies, drain currents, number of fins, and transistor types like FinFETs and nanowires. These works then studied the impact of the elevated channel temperature in small circuits like ring oscillators or SRAM cells. However, state-of-the-art did not consider the impact of workloads on self-heating. To explore the impact of workloads on self-heating, we show the impact in a NAND cell. A NAND cell has 4 transistors, which become hot if a drain current flows through them. However, if this current flows does not depend on the clock frequency as state-of-the-art assumes, but rather on the data applied to the 2 inputs in 1 and in 2 of the NAND cell. So let's consider this table with input data for 4 cycles. In cycle 1, both in 1 and in 2 are 1. Therefore the output of this NAND cell would be low. In cycle 2, in 1 switches from a 1 to a 0, and thus the output switches from a 0 to a 1. This means that the current is now flowing through both upper PMOS transistors to charge the output of the NAND cell from a 0 to a 1. In cycle 3, both values stay the same. This means that none of the transistors switches, and none of the transistors have a current flowing through them except the leakage current. Therefore, self-heating is low. This data might stay the same for multiple cycles. This illustrates how the switching frequency can be much lower than the clock frequency. In cycle 4, in 1 switches from a 1 to a 0, but the output remains high. Therefore, again, none of the transistors really switch, and again, self-heating stays low due to negligible currents, only the leakage current flowing through the NAND cell. The novel contributions of this work are to study the impact of this workload on self-heating. The duty cycle and switching frequency of transistors is obtained from a gate-level simulator running actual software on a circuit. Therefore, contrary to state-of-the-art, we consider not just static cases or simple oscillating cases like ring oscillators, but actual activity. Additionally, we study self-heating in a full processor core instead of smart circuits. This means that we study self-heating in thousands of transistors and again running actual software applications. We do this all the way from standard cells to a full processor core. Together with this information of the duty cycle and switching frequency for these thousands of transistors, we then estimate the elevated channel temperature due to self-heating. If you are interested in the publication, please download it with the digital object identifier link via the QR code on the screen. If you have questions about the publication, please contact myself, Victor van Santen, or my co-author Hussam Amrouch with the email addresses on the screen. Thank you for your interest in this publication and goodbye.